right, ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at rate laws. Now, there's two different rate laws that we are going to get into. The first one is going to be a rate versus concentration relationship, and that is going to be known as the differential rate law. Now, most of the time, the differential rate law is actually just abbreviated as just plain old rate law. And then the other side of this is going to be a time versus concentration relationship. And this is going to be known as the integrated rate law. Now, again, it's very important that right at the beginning we understand we're going to have to differentiate which one of these we're working with. They both have their own little nuances for how we work through and interpret the information. All right? And so first thing we're going to do is we're going to take a look at differential rate law. Now, this is anytime we're going to use the differential rate law a lot of the times here just to relate that rate to concentration, but this really asks the question and answers the question of what if I change this concentration, exactly how does it affect my rate? So if we're looking at a very general reaction, like A plus B gives me C, a rate law equation for this would the general just generic form is going to be rate is equal to my rate constant times the concentration of A raised to some power times the concentration of B raised to some power. Now, it's very, very important that you understand the exponents there are actually my reaction orders. All right? Those are my reaction orders. So X is the order of reactant A, and Y is the order of reactant B. All right? Now, my overall reaction order, which is something that you'll need to get down, your overall reaction order is actually just X plus Y. And so make sure that you get that down. And each X is respective to A, Y is respective to B, and then again, overall is just X plus Y. Now, what are these reaction orders? Well, reaction orders, if you look at the mathematical equation, is just telling me how changing concentration affects the rate. Right? Now, there's three different scenarios that we're actually going to be working with, and it's zero order, first order, so zero order, first order, and second order. Zero order, changing the concentration does not affect rate. That's what you want to get down. First order, changing concentration is a proportional rate change. And then second order, changing concentration is an exponential rate change. And this one's exponential because it looks like this, guys. It's actually x squared. This is just x, and this is x to the 0, right? Or I could put x to the first there. I guess if I wanted to use, like in terms of A, I'd say concentration of A to the 0, concentration of A squared. And so those would be how my concentration would look or how my rate law would look if it was zero order, first order, or second order. Now, anything raised to the 0 exponent to the 0 order is actually just 1. So a lot of the times if something is 0 order, we actually just leave it out of the rate law. And that's actually a pretty common trick for them to test your understanding. The understanding that something raised to the 0 power is just 1. I can leave it out. I don't actually have to write it. All right? And so a lot of the times what we're going to do is we're going to be using table logic is what we're going to say. Now, table logic, I'm going to go ahead and pause the video and put a problem down here for you really quick. All right, and so what I've got here is I've just got a table, and now notice in the table a couple of things. First off, I've got a rate versus a concentration information or table here, and so that puts me again in this differential rate law realm. I know I'm going to be rate equals to K times the concentrations raised to some exponent. So how do I determine what the orders actually are? Well, just like in any good science, if we want to figure out with respect to A, I'm going to hold I'm going to hold B constant, and I'm going to change A. Because by holding B constant, then I've removed B out of the equation, and any change to the rate is actually only due to changing the concentration of A. So what we'll do is we'll look at this very first one. So notice B is constant. What I've done with A is I've cut it in half. Now, I like to always be a positive multiplier, so I'm going to say I'm going to multiply that times 2 going up, and then notice over here I'm going from 5 to 20 as my rate, and so I would say that that is a times 4 relationship. And so again, I've got 2 equals 4. Well, the only way to make that that situation where the change to my concentration, change to my rate are equal, is to say that it's 2 squared is equal to 4. And so I'm going to go ahead and start building my rate law down here and say K concentration of A squared, because I know A is second order because of that exponential relationship. Now the next one that I'm going to do is, again, I'm going to find where A is constant. So I'm going to find where A is constant here, and then I'm going to figure out exactly what happens with B, right? And so if I'm looking here, I'm saying that's times 2. Well, I go over here and I look, that's times 4. So again, I've got 2 equals 4, so that's 2 squared is equal to 4. That means B is also going to be second order. Now, again, for overall order, notice it's just 2 plus 2, and that's going to give me 4. So my overall order for this reaction would be 4. And the way that I would read this, ladies and gentlemen, is this order, or this reaction is second order with respect to A, because by holding B constant, doubling A quadruples the rate. Okay? And very important to listen to the nuance of that explanation. All right? I'll do it for B. All right? So by holding A constant, by doubling the concentration of B, we have quadrupled the rate of the reaction. Therefore, B is second order. All right? And so, again, all you're doing is explaining, holding one constant, changing this, and change the rate that way. That's why I'm saying it's this particular order. All right? Now, the other thing that they might ask us about here and try to get us to do is they want to know units of K. Now, with K, it's always rates are always this change in concentration or change in molarity over change in time. So the trick for K is it's always 1 over time, and then your molarity here is going to be your overall reaction order minus 1. So in this particular case, my overall reaction order is 4. So K is going to be 1 over time molarity cubed, because I've got overall 4 minus 1 gives me 3, and that would be the units of my K in this particular case. And so this here is something definitely you're going to want to know. Writing down the units of K is a very, very common question. All right, so that's it for differential rate law. So again, that's a rate versus concentration. We're going to use table logic. We got 0 first and second order. All right, and again, changing one, seeing how it affects the rate while holding the other one constant. Now, integrated rate law, this is a time versus concentration. Integrated rate law is actually used a lot in everyday life because this is all about, hey, if I take this particular drug, like Tylenol, for example, how many hours go by before I've gone under the minimum effective dose in my body and I have to actually redose the medicine? And so integrated rate laws are going to give me this, hey, at some time in the reaction, what's my concentration that's actually there, right? And so, again, integrated rate law, this is a graphical analysis of data, right? A graphical analysis of data to determine order, and the rate equations are different for each order. I don't have a general rate equation that fits into table logic and everything else. I've got 0 order, first order, and second order, and they all have a different graph and a different equation. So what I'm going to do is I'm going to pause the video and go ahead and write all these out. All right, and so here's the 3 graphs that I'm going to have to be familiar with, ladies and gentlemen. I'd pause the video, get them down, and then keep going. All right, so 0 order, notice this is a concentration versus time graph, right? It's a negative slope. The slope of the line is actually equal to K, and if you look at the equation, you can see it's some concentration at a given time is equal to the negative rate constant times time plus my initial concentration. This A naught, that's my initial concentration that I'm beginning with in the particular reaction. First order is natural log of concentration versus time. This one is the most common one that you'll see is first order, right? It deals with half-life. Half-life is based on a first-order relationship. And notice again, slope is K. It's a negative line, so both 0 and first order have negative rate constant slopes. Although rate constant, this is a common trick, and you want to make this big in your notes, rate constants are always positive. So notice it's negative in the equation. It's a negative slope, but K itself is actually positive. All right? And so again, it's some natural log of concentration at the given time is equal to the negative rate slope times time plus my natural log of initial concentration. So with this one, ladies and gentlemen, you got to pay attention to your algebra when you're solving these out, and make sure that if you're solving for an initial concentration, that you understand when you do the initial algebra here, it's natural log of concentration. You have to actually get rid of that. And then by second order, the last one, this is the reciprocal. This is 1 over concentration, right, versus time. And this is the only graph with a positive slope. And so that's an easy recognizer or easy clue, if you will, to recognize that, hey, this is a second order relationship. And again, it's got its own little nuance of the equation. Now, the equation, I know there are three different equations. They're all in this form of y equals mx plus b. So notice it's my concentration at some given time plus my initial concentration. The slope is your k value, and then x is your time. And so if you just remember the y equals mx plus b and the fact that first order is natural log versus time, zero order is concentration versus time, second order is 1 over concentration versus time, I think you'll be in good shape, ladies and gentlemen. And that's it. Integrated rate law, again, it's just recognizing the patterns in the graph and being able to get those down. And that's it. Hopefully if you had some questions, you got them down. I'll see you in tutorials for those. Otherwise, I will see you in class.